Okay, good evening, everyone. So let's start. So let's quickly review what we discussed in the previous lecture in the earlier in the morning today. So we revisited Fourier series. You have seen this before in your other courses. We started off by first taking a look at again uh, the Fourier series real form, which is how Fourier series generally introduced for the first time, which essentially says that any periodic function of period 2L can be represented as a sum of sines and cosines plus a constant. And there are formulae for these sines and cosines. And then I try to highlight that the key idea is that for most functions, when you, for example, we took this step wave function, and if we do the math, we can get its Fourier series to look like this. And if you if you plot, let's say certain, see, if you try to use infinitely many terms in practical applications, it's not going to happen. You have to use finitely many terms. But the thing is, if you use sufficiently large number of terms in the Fourier series, usually you are able to approximate the actual function quite closely. And I gave an example from my research where you need to parameterize periodic walking trajectories of a walking robot to be able to optimize it. Okay. So there are many applications where you know a function is periodic. You just want to describe that periodic function with finite number of parameters. So a truncated Fourier series is perfect for that kind of situation. And then we went on and in the Fourier series expressions, we just substituted cosine and sine with its complex exponential form. We did the algebra, or I did not do most of it. You can read it here. It's straightforward. And we were able to show that as opposed to the real form where the Fourier series has different formula for the constant, coefficient of sine, coefficient of cosine. In complex form, the Fourier series can be just written as weighted sum of complex exponentials of different frequencies, n pi x by L, where n goes from minus infinity to infinity. And this Cn, this constant or the weight of each complex exponential can be determined by using this one single common formula. So the power of complex form of Fourier series is that it's much simpler, much more compact. And then there was an example that you can work out, and I tried to point out the striking similarity between Laplace transform and the formula for the coefficient of Fourier series. Okay, so for if you think of Fourier series as a Fourier series transform, then these coefficients are the transform quantity. Similar to Laplace transform, that function of S is the transformed quantity. So if you have to compare these two things, you have to compare the formula of the coefficients with the formula of the Laplace transform, and they have quite a bit of similarity. Okay. And indeed, this you will see comes from here only. Then there is a worked out example that is straightforward. You can work it out yourself. And then I pointed out that the key how this Fourier series came out is that in this space of t periodic functions can be treated as a vector space. In this vector space, these are basis functions, and in this vector space, the inner product is defined like this, just integral of the product of one function with the complex conjugate of the other function divided by the time period. So these are all functions with period t. And if you just extend the idea of basis from your familiar three-dimensional or two-dimensional Cartesian space, the component of each function along its basis can be evaluated by just taking inner product of that function with a specific basis function. So the coefficients are essentially the components of those t periodic functions along these basis functions, which are these complex exponentials. Okay, so this is how Fourier series came out. And then I gave you an example that, another vector space that mathematicians have studied is the space of all possible functions on the interval -1 to 1. And one of the basis, orthogonal basis that they came up for this space was this sequence of polynomials called Legendre polynomials, and on this space, the inner product is defined like this. Now, for a space to be vector space, there is a list of properties it needs to be satisfied. For an inner product to qualify as inner product, it has to satisfy certain properties. We are not going into those details. Those are available in textbooks and are usually taught in a linear algebra or mathematics course. This was just an overview. Now I told you that in this story of frequency, our key motivation is to start with Fourier series, then sort of remove some of its imperfections and go to Fourier transform, then remove some of its imperfections and go to Laplace transform. And then Laplace transform we will use to talk about bandwidth of signals, bandwidth of systems. Systems meaning differential equations most of the times. Okay. So let's see what what could we possibly improve about this Fourier series. Now, this Fourier series you can use in all situations where periodic functions are involved. But now in our control applications, we are actually not interested in periodic functions. Our functions actually are aperiodic. Your reference signal, which is that step input or a constant input, that's usually, it's not a periodic function. It just at t equal to 0, it goes up to some desired value and stays there. The response, for example, in that uh, automatic cruise control example, our reference function was something like this, and the response was something like this. None of these functions are periodic functions. These are some general functions. We want to essentially use this to talk about, we want to develop a tool that we can use to talk about the functions we deal with. Most of the functions we deal with are not periodic functions. So let's see what we can do with Fourier series to be able to use it with aperiodic functions. Now, you can actually use Fourier series already with an aperiodic function which is limited to just some finite interval of time. See, Fourier series can be used to sort of characterize or parameterize any function which has a period 0 to t, which has a period t. Okay, it does not put any constraint on what this function should be between this interval. So let's say if you are in a situation where you are interested in a function just on the interval 0 to t, just on the interval 0 to t, and you do not care what happens outside this interval. You are interested in just a finite time duration. You are not interested in what happens outside this function. Then actually this Fourier series can be used to define, to characterize any arbitrary function in between this 0 to t. Just a Fourier series with fundamental frequency 2 pi by t will be able to do that. Okay. Yes, it is true that outside of this 0 to t, that Fourier series will keep repeating for sure because Fourier series is periodic. But let's say you are interested only in the period 0 to t. In those situations, you can actually use to study functions that only matter to you between 0 to t, and in between 0 to t, they can be anything. But see, that is also not we are interested in. Our reference function or behavior of our systems, once they are switched on, they operate for a very long time. A priori, we do not know how long this system will be operated. So we cannot have a fixed T knowledge a priori. We want to be able to use a tool for aperiodic functions of arbitrary duration. So what we do, we study Fourier series and we first notice that within the interval 0 to t, Fourier series can be used to describe any function. Then what we do, we just look at again once again the formulae for coefficients etc. for the Fourier series, and in that we just make this t, capital T, the period to be infinite. Okay. So if we can have a periodic function with period infinite with an infinite period, that essentially is any aperiodic signal. Okay. That means in that period 0 to t, it can do whatever, it need not repeat between that in that interval 0 to t where t is becoming very large. So that is how Fourier transform is derived from Fourier series. Fourier transform is essentially same expression for Fourier series with the time period t tending to infinity. So that is what is depicted here. So this is a periodic function. Okay, we zoom in on just one period of it, and then we just take these limits t to infinity. Okay, and that's how we get uh, the expression for Fourier transform, and that's what we will do. So what we are essentially doing, to go from Fourier series to Fourier transform, we are making t tending to infinity. T tending to infinity means omega tends to 0. Remember, omega 0 was 2 pi by t. So this is basically a limiting operation. So let's go ahead and do that. Okay. So, so that entire derivation is given in just this single slide. That's all we need to know. So see here, so here is that complex form expression of Fourier series. So now all I have done is that I have called that Fourier function f. I have added this subscript t just to highlight that this is a periodic function of period capital T, where where Cn are the complex Fourier coefficients, these are the complex exponentials, and you can solve for each complex exponential by just using the same formula that we derived earlier. Okay, so all I have done, you are supposed to integrate over one period. We have chosen the period going from, we have chosen a symmetric period. It is just convenient. We have chosen a symmetric period around origin, going from minus t by 2 to plus t by 2. And we are calling this function f as f capital T, just to denote that it's a function with period t. Okay. Now let's first look at, so as we take, we go from, so this, in this series of complex exponential, each successive complex exponential has a higher frequency than the previous complex exponential. Let's just compute the difference or the delta omega between these two consecutive frequencies of these complex exponentials. So, so the consecutive frequencies n omega 0 and 2 pi by t. If you try to compute the delta difference between two consecutive frequencies, you just subtract n omega 0 minus n minus 1 omega 0, and obviously it comes out to be omega 0, 2 pi by t. So essentially, what happens also is that as you take t to infinity, the difference between consecutive frequencies becomes smaller and smaller. In this series, let's say we look at this expression, we look at this expression, as we start making t larger and larger, what is happening in this summation is that these consecutive frequencies are moving closer and closer. It becomes like essentially an integration. This n omega 0 in the limit t tends to infinity, they become so close that this summation you will see going forward will convert into an integral, because that omega, instead of being discrete, those consecutive omegas become closer and closer to each other and they become a continuous function omega. So we will see that later. So what we do is that in this expression for Cn, okay, so we want to just work, we just substitute this 1 by t as omega 0 by 2 pi. Doesn't, they are related by this expression, we can, this is just a constant, we can do that. Also what we do, we substitute this expression of Cn right here in this Fourier series. So by doing so, you get ft. So this is that Cn that we have substituted. In this Cn, we have replaced that 1 over omega t by omega 0 by 2 pi. And we still have this summation. Now, in this summation, we will we will do the modifications that we are interested in. So Now in this summation, as t goes to infinity, what happens is these n omega c, this integral is an integral over dt over time. So in this integral, this n omega 0 and this n omega 0 is not involved actually. Okay, just the n omega 0 part is not involved. So these n omega 0 in this summation become like very close to each other. This omega 0 becomes smaller and smaller because this omega 0 is actually 2 pi by t. This omega 0 starts acting as d omega. It becomes very small. Okay. These n omega 0, instead of being discrete frequencies, they become essentially continuous, some continuously changing variable. We call that continuously changing variable. We replace this n omega 0 by some continuously changing variable omega. And we change this summation to a continuous integration going from minus infinity to infinity. Once we do that, by just appreciating the fact that as t was going to infinity, this omega 0 was becoming smaller and smaller. These n omega zeros were drifting closer and closer to each other. They were behaving like a continuous function of frequency omega. We replace that and we get this equation. And this equation is the equation of your Fourier transform, simply obtained by making t going to infinity in the Fourier series. So in this expression, this part, this part is called capital F omega, or actually this, not the whole part, just this integral, just this integral. This integral is called f omega. Okay. This is called Laplace transform of a function. Okay. And there is no, this function ft need not be periodic. It's a general function. Okay. And so if you have a function ft, you want to compute its Laplace transform, you evaluate this expression. So what you will get is going to be a complex function of omega. If you have the Fourier transform, you want to evaluate, get back the original function, you evaluate this integral, and you will get back your original function. Now let's talk about the meaning of this Fourier transform. What does this f omega mean? Okay, it has the exact meaning that Fourier coefficient had. So Fourier coefficient, let's review what Fourier coefficient meant. Fourier coefficient AK, which was this expression, it was the weightage of AK was sort of the contribution of AJ e raised to the power minus I j omega k omega 0 t in the original function. So the AK was the coefficient of this complex exponential. This complex exponential was a frequency k omega 0. So this AK was telling you how much the frequency k omega 0 is contributing to your original function that you started with. So if AK was small for a certain number, you would know that that particular frequency k omega 0 is not contributing that much to your function. Similarly, you compute for an aperiodic function, you compute its Fourier transform, you will get a function capital F of omega. In this omega, now you can substitute what in this function of omega, capital F omega, you can substitute any frequency omega that you want, 1 hertz, 100 hertz, 2 kilohertz, and you will be able to compute a number. That, or actually it will be a complex number. So that complex number is going to have a magnitude and a phase. Its magnitude is going to tell you how much contribution does that particular frequency have in terms of in your or in that aperiodic function ft that you started with. So the key idea here is that Fourier series sort of is based on the idea that all functions of period t can be represented by complex exponentials having these discrete frequencies k omega 0, where omega 0 is omega pi 2 pi by t. Okay. Then people thought ki if you are able to express periodic functions by these complex exponentials or sine and cosines, can we express aperiodic functions also as sums of complex exponentials and sines and cosines? And the answer is yes. So what essentially Fourier transform is telling you is that you can take an arbitrary function and you will be in many sometimes these integrals do not exist. Okay. And that is a drawback of Fourier transform. For many functions, it does not exist. But for the function for which this transform exists, what it is telling you is that you are again able to express your original function ft as a sum. See, this outer integral is essentially a sum of these things. What is inside? This is a sum of some coefficient times ei omega t, and omega goes from infinity to infinity. So what Fourier transform is telling you that yes, you can express arbitrary aperiodic functions as sum of complex exponentials, but it will take all possible frequencies to be able to do so, not just multiple of some discrete frequency, because there is no special frequency here. These are aperiodic signals. So to be able to express aperiodic functions, you will need all possible frequencies to express them. But luckily for us, most signals will not have all possible frequencies. For some frequencies, this f omega will have very small magnitude. It will not be contributing significantly. And that is what we will sort of exploit in our control design. So we already talked about that, sensor noise is difficult to deal with. Reference signal is difficult to deal with. So the reason we are able to deal with is that if you take the reference signal, okay, let's say we call the reference signal RT and the sensor noise ST or NT. You take those reference, a typical reference signal and a typical noise signal, and you do their Fourier transforms. It will turn out that these f omega for the reference signal and the noise signal will be such that f omega will have higher magnitude in different frequency regions. So you are able to work with them separately. Okay. So, so Fourier transform for a general signal is able to tell you what are the frequencies present in that signal, which frequencies are important, which frequencies are not important. Okay. So that is what you need to remember. So when you compute this f omega, you substitute any frequency omega in this, you will get a complex number. Its magnitude tells you how much important it is, and its phase also tells you some things. We will discuss later how to use phase. But the more important thing is the amplitude. If the amplitude is small, okay, for a particular frequency, then we don't need to worry about the phase. Only if the amplitude is large, then we need to worry about the phase. Okay, we are going to get into those discussions later. So when I am in full screen, I am not able to see if any of you is raising your hand. So if you have questions, uh, you can just unmute yourself and ask your questions. Okay. Are there any questions so far regarding this derivation? Okay. So you can ask me later as well. I will proceed for now. So we have now moved from Fourier series to Fourier transform. And the main shortcoming of Fourier series that we solved in doing so is that you can use Fourier series to find frequency content of periodic signals, but you can use Fourier transform to find frequency content of any signal. It's just that the Fourier transform for that signal should exist. And it indeed does not exist for many signals. We are going to talk about those signals as well. Okay. But let's first look at a few examples. Okay. So a very popular, so the two most popular functions or test functions in control theory is the step function, which is of sometimes called ht, and a Dirac delta function, which is called delta t. These are the two most popular functions. Okay. So in this uh, example, we are trying to derive the Fourier transform of a delta function. So see, delta function, is essentially a very sharp peak. And what we know is that the area under that peak is 1. Okay. And that peak is happening at 0. Okay. So we can approximate this Dirac delta function as a triangle like this, starting at 0, whose base is of length delta and whose height is of length 1 over delta. So the area, no matter what value of delta you choose, the area of this triangle is 1 by delta times delta, which is 1. So this capital delta function in the limit delta goes to 0 is actually it becomes a direct delta function. Okay. So what we will do is we will compute the Fourier transform of this function first, okay, with some finite delta. And then we will take the limit of that Fourier transform with some finite delta to delta tending to 0. Okay, that's how we will compute the Fourier transform of this delta function. Okay, so you write down the expression, you just use the expression that was derived on the previous slide. So you have to use this expression, integral going from minus infinity to plus infinity, ft e raised to power minus a omega t. Now, what is our ft? That function with capital delta. It is actually 0 everywhere except in this region 0 to delta. So R, when we are evaluating Fourier transform of that delta function, we do not need to integrate from minus infinity to plus infinity. We can simply integrate from 0 to capital delta. And in that capital delta, this ft is simply 1 over delta, which is a constant. So that is what is done in the next slide. So you essentially just integrate 0 to delta, and the integral is just that function is just 1 over delta multiplied by e raised to power minus j omega t dt. Okay. So when you are computing this integral, you can actually take this 1 over delta is a constant. You can bring it out. You can just compute 1 over delta integral 0 to delta e raised to the power minus j omega t dt. This is a very easy integral. So this is just e raised to power minus j omega t by minus j omega 0 to delta. So you get 1 over delta e raised to the power minus j omega delta minus 1 by minus j omega. So you swap, you take this sign up, you get 1 minus e raised to minus j omega, and at the bottom you combine this delta here, you get j omega delta. So now see, you have a situation where if you substitute delta in this expression, you will get 0 over 0. Okay. So we cannot directly substitute 0 to evaluate this limit. So what we will do to evaluate this limit is what you used to do in your JE time preparation. We will use the L'Hopital rule. Okay. The L'Hopital you said that when you are encountered with a 0 by 0 form, you differentiate the numerator and you differentiate the denominator with respect to the variable, which is delta in this case, and then substitute whatever you want to substitute. So if we differentiate the numerator, we will get minus, okay, my pen is stuck somehow. Okay, I think my pen battery has died, so I will just use my mouse. Okay, so if we it has come back. So if we differentiate the numerator, we get minus j omega, and then e raised to the power minus j omega delta. And in the bottom, we get j omega. So this becomes plus j omega cancels. You substitute delta equal to 0, you get 1. So the answer is 1. So the Fourier transform of a Dirac delta function is 1. So what does that mean? That means that this Dirac delta function, as simple as it sounds, it has all possible frequencies present in equal proportions. Okay, because this is constant 1, so this f omega is equal to 1. No matter what omega you substitute, you will get a 1. So this Dirac delta function is a function which has all possible frequencies summing up to give you this peak, and all these frequencies have exactly the same contribution. And that is what is exactly what makes this Dirac delta function popular, because what situations where this is used is a test function to know things about the system. What kind of things can we possibly know? So there is something called an impact test. So this Dirac delta function is like an impact. If it's like you are delivering some impulse to your system. So there is something called an impulse test or Hammer test, where let's say you have a structure. That structure could be anything. Let's say there was a machine. You made a structure of a machine. Uh, Now, all structures will have some natural frequencies. You can, of course, try to do modeling and try to find it. Very often, you want to find natural frequencies experimentally. So, how do you find natural frequencies experimentally? You do an impact test. Impact test is essentially applying a direct delta function to that, or a forcing in the form of a direct delta function or an impulse to that structure. So that forcing essentially has all frequencies. And when you apply all frequencies to a structure, that structure will vibrate only on its resonance frequencies. This Dirac delta function will excite all resonant frequencies in that structure. So you can put some accelerometer on that structure, record the time series from the accelerometer. So that accelerometer now will have only the resonant frequencies. And that accelerometer time sequence is going to be some function f of t. You do its Fourier transform. When you do its Fourier transform and you plot it, so that Fourier transform is a function of omega. You plot it as a function of omega, you will see things like this. That is going to have peak at certain locations. Those locations are going to be the resonant frequencies of that structure. And you will tell your client that if you operate these machines, stay away from these frequencies. So these resonant frequencies are often determined by using Hammer tests, which is essentially applying this delta function, or essentially applying an excitation of all frequencies. All the system will select just the frequency at which it can resonate. All other frequencies will slowly die down because system has damping. Just the resonant frequencies will stay, or they will stay for longer. Okay, so a practical application of direct delta function. Okay, so when you see direct delta function Fourier transform 1, you know it has all frequencies. Okay, another example of Fourier transform. So this time, so most of the times in controls, we are actually interested in starting our control system at some time t equal to 0. Usually before that, everything is 0, and starting at that instant t equal to 0, so things start changing. Okay, so that is the kind of function we have taken here. So this function is 0 for t less than 0 and is e raised to power minus alpha t for t greater than 0. Okay. So if you plot it, it looks like this. So you can write these kind of functions using step functions or heaviside functions. So for the place from where I have taken this example, they used ut to denote heaviside functions. So to write this kind of a function in a compact form, you can write it as ft is e raised to power minus alpha t times this step function. So if you have to compute its Fourier transform, nothing special. You just compute that integral that we had before. Okay. This, this integral. Okay. Here you are integrating from minus infinity to infinity, but remember our function actually starts at 0. So we can just integrate from 0 to infinity. We don't, for this particular function, we don't need to integrate from minus infinity. So that is what is done here. You are integrating from 0 to infinity. And in this region, this function is just 1. This ut is just 1. So all we have written is e raised to minus alpha t. We can combine these things. It becomes e raised to power minus alpha plus I omega times t. So this is a simple integration. You just get the same exponential function again divided by the coefficient of t, and then you just put the limits at t tending to infinity because it is given in the question that alpha is a positive constant. As t tends to infinity, the first term goes to 0, and as t tends to 0, the second term in the numerator goes to 1. So you get 1 over alpha plus I omega. So luckily for us, this particular function has a Fourier transform which exists. This is an aperiodic function that starts at time t equal to 0. Now, what can we say? The interpretation of this Fourier transform is the same what we told you. It is telling you how much contribution a particular frequency provides. And just by looking at this f omega, we can tell. See, so it's if we this is a complex number, it has a phase and a magnitude. So its magnitude is 1 over alpha square plus omega square, right? Under root. And its phase is negative tangent inverse omega by alpha. Okay. So this is just complex algebra that you have done before. So you can look just by looking at this magnitude, you can tell that as the frequency will increase, this magnitude is going to decrease. So this is also a type of function where higher frequencies contribute less. Okay, this for very large frequencies, this number will become very small. This alpha is staying constant, just this omega is changing. Okay, and the phase is doing something. Okay, so in the next slide, this magnitude and phase is what is plotted here. And this is just called polar form of Fourier transform. So we get that f omega. It's it's uh it's magnitude. So these are the same phase and magnitude that I wrote in the previous part. These things are plotted here. Okay. So this is plotted here, and as we expected, we can see that as frequency increases, the contribution is going to 0. And here also, as frequency increases, the phase is changing. We will talk how to use phase later. Okay, we'll give actually physical meaning to this phase as well. Not right now though. Okay, phase is something. So, but what this plot is telling you is that if you choose frequencies just in this region, approximately, you are able to describe your signal quite well. Frequencies beyond that are not contributing that much. So that is the kind of information we want to glean from these transforms. Okay. And this sort of range is sort of called, this is what is called the bandwidth of the signal. Okay. Or up to what frequencies, up to how many, what frequency What is the highest frequency that you need to sort of sufficiently to describe a particular signal sufficiently well? That is essentially what bandwidth is. So these kind of plots give you an idea of what the bandwidth of that signal is. Okay. We'll use these ideas to talk about bandwidth of systems as well. Okay. So now let's talk about some functions for which. So we gave you two examples for which Fourier transforms exist. Okay. But the problem with Fourier transform is that it does not exist for all functions. The reason it does not exist for all functions is because of this integral itself. Okay. So this integral is an integral of an oscillating function. Okay. And it is getting multiplied by something. Depending on what it gets. So nothing is decaying here really. Things are oscillating. Things are not decaying. So as t goes to infinity, things will not die down. Things may not die down. Okay. Things may things may actually blow up. All integrals which are integrated over infinite time limits have a very high possibility of exploding. Okay. Unless what you are integrating is of decaying nature. What we are integrating here in general is not a decaying nature. This part is oscillating, it is not decaying, and this part can be anything. So wherever they combine such that they can easily combine to form a combination which can explode. Okay. So this Fourier transform does not exist for many functions. Okay. And we are going to look at some of those kind of functions. And that is why we need Laplace transform. Laplace transform also does not exist for many functions, but it exists for a larger class of functions compared to Fourier transform. Okay. That's the key advantage of Laplace transform. So people modified Fourier transform itself into something that we now know as Laplace transform. Okay. And we are going to do that. We are going to learn how to do that. First, let's look at some functions for which Fourier transform does not exist. And the problem with Fourier transform is that it does not exist even for simple functions like a linearly increasing functions. And a linearly increasing function is definitely something we will encounter. For example, if you want to track, if you want, for example, if you want a system to take to when you are launching a rocket, is displacement. We want to control its displacement or the height. That height is continuously increasing. It's actually increasing much faster than linear. Okay. But we want to, the reference signal there is definitely an increasing function. Linearly is much faster than a linear. So many a times our reference functions or the reference trajectories that we want are actually polynomials or increasing polynomials. Okay. So ht times t is definitely a type of function that we need. And even for this simple function, Fourier transform does not exist. And you can check that it does not exist just by trying to compute the Fourier transform. So this Heaviside function is also to tell you that this function is starting from t equal to 0. And the reason we are putting ht or Heaviside function in front of most of the examples we are looking at, because in controls, those are the kind of functions we are interested in. Functions that actually start operating at t equal to 0. Before that, everything is 0. Okay. So So when you are evaluating the integral for capital F omega, you can start integrating at t equal to 0 as opposed to minus infinity. So you integrate this. Now to integrate this, you have to use integration by parts. Remember that you studied in JE days. So if you have to integrate something like this, there are two functions. What you do, you keep first function as it is, and you write down the integral of the second function. This is the integral of the second function. Then minus integral of the derivative of first function, which is t is 1, times the integral of the second function. Okay, which is same as this, which is written here. So and with proper limits, 0 to infinity. Now in this, the first term itself, is not converging. As you take t to infinity, this keeps oscillating and this blows up. Okay. So, so this is this is not working. So Fourier transform does not exist for a simple linearly increasing function. So which we definitely need. We want to be able to deal with polynomials. It does not exist even for t square, or for that matter, any polynomial. Okay. So not a good thing for us. Another function, it did not exist for a slowly increasing linear function t. There is no way it can exist for an exponentially increasing function, at. Okay. Because an exponentially increasing function, when integrated over an infinite time period, will definitely explode. But you can check that by again writing down the formula for the Fourier transform using the expression e raised to power at times e raised to power minus j omega t. You get this simple. This is a pretty simple integral. The integral is just whatever the exponential is divided by the coefficient of time. And in this, as you put t tends to infinity, this a is greater than 0. So this thing just explodes. So this Fourier transform does not exist also. So Fourier transform is very useful because it has the capability to tell you what frequency content your signal has. But the problem is it does not exist for many signals. So what we want is we want to have a tool which, like Fourier transform, tells us what is the frequency content of the signal and hopefully exists for a larger class of functions or signals. Okay. And Laplace transform is that kind of a transform. So for these two transforms these two functions that we just discussed, this exponential function and this linearly increasing t, for both these functions, Laplace transform exists, but Fourier transform does not. And that is why we tend to use Laplace transform much more than Fourier transform. Okay. So now that I have set the base for you, let's quickly summarize the key shortcomings in Fourier transform. So Fourier transform essentially is an integral of an oscillating function over infinite time interval. So it can diverge very easily. And we saw two examples, exponential function and t. Also, Fourier transform is designed for the interval minus infinity to plus infinity. But the interval we are actually interested in for control application is t equal to 0 to t equal to infinity. Our control systems will always start from 0 at some time instant. So it will be better that if we can have a tool specifically designed for those kind of situations, starting at t equal to 0. Okay. So that tool is Laplace transform. It starts at t equal to 0, exists for much larger class of functions compared to Fourier transform, also tells you about frequency quadrant. Okay. However, that does not mean Fourier transform is completely useless. Fourier transform has many applications in solving boundary value problems with PDEs, in heat transfer, diffusion problems. There is a large class of problems where Fourier transforms are somehow turned out to be superior than Laplace transforms. So Laplace transforms are suited for initial value problems where you are starting at some time instant with some initial values. Whenever you have boundary conditions, for example, in PDEs, there are boundary conditions, Laplace transform is not suitable. Okay, or Well, in some situations it can be suitable, but in most situations it's not. So next, what we will do with that background, having some idea. So we are on our journey. We started with Fourier series. We pointed out some shortcomings. We needed something that can be used for aperiodic signals that turned out to be Fourier transform. Fourier transform does not exist for many things. So now we want to convert our Fourier transform into Laplace transform. That is what we will do on this slide. Just this one slide has everything that takes us from Fourier transform to Laplace transform. Okay. So what we do, so in this equation, what has been done? So there is some function, the time function for which I was using ft earlier. For here we have used capital Ft. Okay. And see, this was the Fourier transform of ft. Okay. And then to go back from the Fourier transform, we could, so let's say we call this f prime omega. I cannot use capital F because I have used capital F symbol here. So this capital F bar omega is the Fourier transform of this function capital Ft. To go back from Fourier transform to the actual time function, we can use the inverse Fourier transform, which was also derived in the previous slide. So what is done here in this expression is in the same equation. I will just take you back to the slide where we derive Fourier transform. So my pen has stopped working again. So see here, this ft we separated out when we derived Fourier transform Fourier series. We had this expression, which was a double integral. So ft was appearing here as well as here, and we separated out this part as capital F omega here, and then ft can be recovered from capital F omega by using this integral. Okay, so in that derivation that we are doing, we are actually started with this equation, where we have written one equation, ft is equal to the integral of this its own Fourier transform, and that Fourier transform is also written in terms of that integration of that ft itself. That is the starting point for deriving the Laplace transform from Fourier transform. So the thing that we will do here, okay, is see this capital Ft. We can choose to be anything. We are the ones saying that we want to compute a transform of some function, capital Ft. And what we want is that this integral that we have written here, we want it to somehow converge. It was not converging earlier because in both situations that we saw earlier, with t or exponential at, these were exploding functions. They were increasing with time. So the Fourier transform integral did not converge. So to get rid of this problem, what we say is that we will define this capital Ft as a new function, e raised to the power minus gamma t, small ft for t greater than 0 and 0 for t less than 0. We can, this equation written here is true for all possible capital Ft's. Okay. We we are choosing this capital Ft to be this function. The nice thing about this function is that it is 0 before t equal to 0. That is the type of function we are interested in for controls. And for t greater than 0, it has some unknown function ft, which can be the function that we are actually interested in, multiplied by a decaying exponential e raised to the power minus gamma t. So this gamma t is like a design variable. We can choose it to be as positive as needed, such that this product e raised to the power minus gamma t ft decays sufficiently for these integrals to exist. Okay. So we have given ourselves a choice of a parameter gamma, which we can choose to be as positive as needed, such that this exponential decays fast enough for this capital FT to decay. Okay. So, what we have done in the next step is we have substituted this function, this choice of capital FT in this expression. And when we do so, so this function can be written actually as capital HT times FT times e raised to the power minus gamma t. What we have done is that e raised to the power minus gamma t that was supposed to be here, we took it on the other side. And when we took it on the other side, it instead of becoming e raised to the power minus gamma t, it became e raised to the power plus gamma t. Now this integral, the outside integral, was an integral over d omega. T is a constant for this outer integral. So this e raised to the power plus gamma t here, we can actually take just inside the outmost integral. It does not cause any problem. We can combine it, combine that e raised to the power plus gamma t with this e raised to the power I omega t, because for this integral is with omega, t is a constant. Okay. And we substitute this f here also with this function. Okay. So here there was a negative sign here already, e raised to the minus omega t. So there also we combine that gamma t with that omega t that was already there, or gamma tau with omega tau. So you get e raised to the power minus gamma plus I omega tau plus gamma plus I omega t here. And then we say that this gamma plus I omega, okay, this we are going to call, this we are going to call as S. So now you remember S. S is coming from Laplace transform. So we substitute this S everywhere. Okay. So we get HT times FT is equal to, so we get an e raised to the power minus S tau F tau here, e raised to the power ST here, and we have substituted this d omega also. We differentiate this, we get ds is equal to I d omega. Because this gamma is a constant, you choose this just once to make sure that this decays. This is not a variable, it does not change. Okay. This is a constant that you have chosen. This is a designed variable. Omega is the variable that changes. Okay. In this Fourier transform, omega is what is changing. Gamma is a design variable which does not change. You choose it to be something. So ds is d omega. So this d omega is written as ds over I. So ds over I, that I comes out. So this expression gets simplified to this. So this is actually your nothing but your Laplace transform. This is nothing but your Laplace transform. So what you see here, this portion is the Laplace transform of your function S. So we call the Laplace, let's say we give f bar S. So we define Laplace transform this function as this integral. We call it f bar S. This is just 0 to infinity ft e raised to minus st. And inside this S, there is a design variable gamma that we choose for it to be whatever is needed to make this integral converge. So now you have a design variable that you can choose such that this integral converges. That is the power of Laplace transform. That omega in there is still the frequency content of the signal. Okay. That is still the frequency content of the signal. And this outer integral gives you a method to recover the original function out. Let's say if you know just this f bar s, then this htft can be evaluated by substituting that Laplace transform, multiplying it by h over st, and doing an integral. So we changed the limit also. So these limits were limits of omega. Okay. So, but now we are integrating over S. So as omega goes from minus infinity to infinity, S goes from gamma minus I infinity to gamma plus I infinity. Okay. So this means you write down this complex function and integrate it over a line starting from at a distance gamma from the vertical axis, going from minus infinity along this line to plus infinity. So if you carry this integral, you can recover the function back. But the point is you never carry, you use this often to compute Laplace transform of a given function. But this reverse, you never use this integral, you just use Laplace transform tables. So you have standard Laplace transform tables, you will use those to compute Laplace inverse because this is too tedious to do. Okay. But what we have achieved in this single slide is we have converted our Fourier transform into something much more powerful Laplace transform. It is more powerful because it has this design variable gamma, the real part of S. Then you can choose whatever you want it to be to make sure that this integral converges. We will do several examples of Laplace transform. You have done many before already, I'm sure. And it still has the frequency content omega in it. The imaginary part of S is the frequency content of the signal. So we will learn how to use Laplace transform to make inferences about frequency content of the signal. So we will continue to, from this point on, we will continue talking about Laplace transform. We have completed our journey from in the morning, we started with Fourier series. Then we talked about Fourier transform. And now we have derived Laplace transform from Fourier transform. So these three transforms, Fourier series transform, Fourier transform, Laplace transform, they are all sort of parent child or brother sister, whatever you want to call them. Very, very related. Okay. So this is all I wanted to cover in this lecture. Do you have any questions? So you can ask, I will stay online for some more time. You can ask me questions. You can ask me questions later as well. As I said, I will upload the video of this recording on Moodle. So you can take a look at it later as well. I will stay online and you can ask me questions, but I am stopping the recording.